Thank you very much for the introduction. It's really a pleasure for me to be here. As Emily mentioned, I'm working in the computer vision group in Never Labs Europe. And I'm going to talk about visual search today. That's one of the many exciting projects we're working on in the computer vision group. And maybe I can start by telling you a little bit about where I come from. So I work for Never Labs. That is an ambient intelligence company focusing on many topics like autonomous vehicles, artificial intelligence, robotics. And I come from the European lab of Never Labs. So we are located in Grenoble. That's where we work, basically. And I'm going to talk about visual search. It's probably a good idea to start with an introduction on what this is about. So we assume we have a large data set of images, potentially very large, and we want to query this data set. And a very intuitive way to make such a query is to show an image to the system, and we would like to retrieve images that are relevant in our data set. And of course, we cannot compare directly pixels. That wouldn't work for our task. What we're going to do is to represent this image with a visual fingerprint or visual signature that captures all the information we need to do this retrieval task. And this visual fingerprint usually takes the form of a vector or multiple vectors that capture all the relevant information. Once we have this correct representation, the one we need for our task, we simply have to do the same. So we assume that we've done that offline. We have extracted all the descriptors of all the images in our data set. And because the representation is appropriate, we simply compare the representation of the query with the representation of all the images, and we check which one are relevant. And that's simply what we return in our system. So in that particular example, we queried the data set with a picture of the Eiffel Tower. And because our signature is built properly, we've recognized other instances of the Eiffel Tower under completely different conditions, but we retrieve the same object. So this is what visual search is about. And visual search has many applications. I'm going to give you a few examples. The first one is probably the most known one, is reverse image search. When you query for an image, you usually type text. But another way to query for a system is to give such an image. For example, you're interested in this particular lamp, so you'll select this area, and what you want to do is retrieve other images of similar lamps, because that's what you're interested in. Another application is annotation transfer. Let's assume you have this image on the top, and you don't know where it has been taken. You don't know where this tower comes from. If you assume you have a large collection of geolocalized images, you compare the signature of that image with the signature of your entire data set, and you match with one of the images, so you can transfer the GPS information, and you know this tower has been taken in Korea, in Seoul. Another obvious application is copy detection. And today, in this presentation, I will talk about visual search and go through 3 examples we've been working on in our group: instance-level image search, person search, and semantic search. So these are the 3 parts I'm going to talk about today. Let's start with instance-level image search. That's the example I gave you at the very beginning. We have a query that contains one main object, in this case a landmark, and we want to retrieve all the images that contain this exact same object. And for that, we are going to build an appropriate representation to do this task. So this has been studied for quite some time. And what is important to note is that when we started this work some time back, it was already after deep learning made a great impression in computer vision. Many tasks got greatly enhanced by using deep learning. So image classification was the first one, and then it was closely followed by object detection, pose estimation, segmentation. So all these tasks were greatly improved with deep learning. But there was one task that we were interested in for which we thought the results were disappointing. For image retrieval, on most of the benchmarks, the best methods were still working on local description, extracting interest points, and doing a geometrical verification on top, which is something that is extremely powerful, but that requires to store a lot of information, and that's also more costly. So That's a bit disappointing, and we really wanted to understand what was going on. So when we started this work, that's the first question we asked ourselves. Why deep learning did not work so well for that particular task of instance level retrieval? And we came up with 3 things that we thought was a limitation of the existing methods at that time. The first one, the training data. Most of the approaches that were dealing with instance level retrieval were using deep learning features pre-trained on ImageNet, a very large data set that was created for classification. So if you train a representation to generalize inside one category, it's not so good if what you want to do is to discriminate between different instances of that category. So that's probably something that is not well suited for the task. The second thing we looked at is the fact that most of the existing approaches would take architecture that takes small images with lower resolution, sometimes distorting these images to make them have a fixed aspect ratio because it was easier, but this makes the detail disappear. And we really believe that retrieval needs high resolution images and undistorted images to keep the details. Finally, the training objective itself. Because when you apply deep learning for retrieval, you are training a representation. So there's some learning involved. And most of the approaches would learn using a classification loss. And we're not doing classification here, we're doing retrieval. So what if we design a training mechanism that is suited for that task? So that is 3 limitations we thought would prevent deep learning from working as well on retrieval as it should. So now that we've found these potential issues, can we build a visual signature that is tailored for instance retrieval? Can we solve these issues? So in other words, can we learn a representation that is exactly suited for this task we want to achieve, instance retrieval? And the answer is yes, if we solve these 3 things. So if training data is available, the network architecture captures the details, and if the training focuses on retrieval. And I'm going to show how we solve these 3 things. First, for the training data. We didn't start from scratch. We didn't build a new training set. We started from something that existed, that was proposed in 2014 by Babenko and colleagues. A landmark data set composed of 200,000 images, and that was composed of about 600 different landmarks. This data set is great because it contains all the information we need, but it's also very noisy. So if we look at one example, this category, which is, I believe, simple cathedral, you have a few images that are really prototypical views. So they're really the kind of images we would like to work with to train. But you also have things that are happening inside the cathedral, which is not so nice and not so useful for recognizing it. Even worse, you have images that are simply wrongly labeled. So what we propose to do is to start from this noisy data and to automatically clean it. And to do that, we used the costly method, but still that are working extremely well, the one that are based on interest point detection and a geometric verification on top. So by doing that, automatically, we selected a cluster of images that were geometrically verified. So we knew that all images were consistently correct with each other. And on top of that, as a byproduct, we even had bounding box annotations. So the idea at the same time is to produce a rough estimate of where the landmark is located in the image. And that was all obtained automatically with this interest point-based technique. As I said, a bit costly, but you do it once for all, and then you have your clean data set, you can start training with that. Then, what kind of architecture can we use? As I said, most of the existing architecture would focus on smaller images, maybe distorted images. There was one notable exception when we started this work. It's the work from Toleas and colleagues, and they proposed an architecture that could work with images of any size and any aspect ratio. And they managed to do that thanks to a region pooling mechanism that could treat any image as input, but then because of this region pooling mechanism, at the very end you have one fixed length representation. So that's very good. But the way it was used only as a local feature extractor. So CNN were used to extract features, and on top of that, they were applying normalization and aggregation of the features without any learning. So because it was done as a post-processing, there's no possible learning. But now if you look closely at this architecture, what we observed is that these aggregation steps can be actually included as part of the architecture itself. And every step is differentiable. So it means that if we wanted to, we could train the model end-to-end, including updating the weights of the convolutions to make these weights correctly suited for the instance level task. So that's exactly what we did in our training framework. As I said, most approaches before were training with a classification loss. But what if we want to train for the ranking task? Because what we want to do is retrieval, so we want to learn how to rank images properly. So we proposed this three-stream Siamese network architecture together with the RMAC descriptor, the descriptor I showed before. So you recognize the descriptor that is here in one branch. We have 3 of these branches, which mean that at train time, the deep architecture is going to look at 3 images. 1 query image, 1 relevant image for that query, and 1 non-relevant image. And then we can look at the representation that is obtained. So the final representation is here. It's obtained at the end of this RMAC descriptor. These 3 representations are considered by our loss. And if the query image is close to the relevant image, that's fine. If the non-relevant image is closer, then the loss is non-zero, which means that at train time, it will trigger an update of the weights of the convolutions and also of the fully connected layer to better build our representation. So what does this triplet loss looks like? Well, if we look at it, the mathematical formulation, we have our query image, we have a positive image, so it's an image that is relevant for the query, same building, and we have a non-relevant image. And the loss is just making sure that the similarity between the query and the relevant is larger than the similarity between the query and the non-relevant by a margin. If this is not the case, the loss is non-zero. It means that the weights get updated. This is how training a deep network works. So that's for the training part. So now to summarize what I showed you, we started looking at this instance level retrieval problem, and we identified 3 things that were limiting previous methods. The first one is the fact that features were pre-trained on ImageNet. That is not good for intra-class discrimination. That's why we proposed to use a different data set of landmarks, and we started from an existing data set that we automatically cleaned. Then we, instead of using an architecture that loses details, we use this architecture that preserves image details because it really pays attention to everything, takes full images and extracts regions. And finally, to train this representation, we use this Siamese network that is taking 3 images at the same time and is learning how to rank images properly. So that's for the summary. Now, this is how it works and how we train. What does it mean to train a network? Why is training for ranking a good idea, and why is training for landmark dataset is a good idea? Let's see visually what it means. So let's look at one given neuron. This is showing the regions in the images that most strongly respond to this one neuron. So we see that these neurons tend to fire on like head and shoulders, maybe of people wearing formal clothes, maybe bow ties, right? So that's the kind of pattern that are chosen by this neuron. This is a neuron after training on this ImageNet classification. Now we're going to take this network and fine-tune it for the ranking task. So the neuron gets actually repurposed to detect this kind of pattern. So the same neuron is now more specialized for what we want to do, this landmark retrieval task, and now it fires on dome structures. Let's look at another example. We had this neuron that was selecting a waist of people wearing t-shirt and blue jeans most of the time. That's a neuron that is produced by classification pre-training on ImageNet. And now the neuron gets repurposed to find this kind of pattern where you have 2 windows on top of towers. So you might think that visually it's a little bit similar, but obviously it's much more specialized to what we want to do. And here's a third example. We had some kind of bird neuron, I would say, and that gets repurposed for this kind of pattern in towers. So that's qualitatively the kind of thing that happen in neuron when you fine-tune for the retrieval task. Another observation we had is the fact that this standard RMAC descriptor, well, as I said, it's pooling regions. That's why from images of any size, it can have this global representation. But now it's using a regular grid, which means that it's looking at large regions, and then it's going to look at smaller regions, and it's going to cover the entire image. And as you can see, some of these regions are completely looking at background. And only a few of them really focus on the landmark. So that's an issue. So that's another question we ask ourselves. Is there a way we could extract only interesting regions and not focus on the background? So in other words, can we learn where to pull the regions instead of taking everything? And once again, the answer is yes, if the right training data is available, but also if the network is adapted accordingly. So for the training data, remember, we had our clean landmark data set, where we had these 40,000 verified images. And as a byproduct, we could predict bounding box annotations by just looking at where the interest point would fire. So we have an estimate of where the landmark is. We're going to use this annotation, although it's not perfect. It has been generated for free. And we're going to train a region proposal network. So we have our image. We know where the landmark is supposed to be. And we have this region proposal network that learns where to pull regions. And then we have this second loss that is really focusing on how to extract the regions. And just to show you what kind of, what is learning. So for all these 4 images, you see the green bounding box. This is where the landmark is located. And you see the kind of response the regions get thanks to this region pooling network. So more red means more likely to contain something interesting. And you see that it kind of focuses on the landmarks, right? Or at least on the buildings. And it's removing some of the background. So now if we use these to pull regions, instead of taking everything inside the image, we see that we'll get regions that are more focused on what matters for what we do. Landmarks. Next obvious question is, okay, sounds nice on paper, how does it work compared to previous approach? Let's compare on standard benchmark to see how good it is. And to do the experiments, we used a bunch of standard benchmark dataset that are used by the entire community and people publish on this dataset. So we could compare to the most recent works. And I'm going to show results for 4 of them. I'm going to start with the Oxford dataset that has 5,000 images of different landmarks. And there's a second flavor of this Oxford dataset where on top of that we had 100,000 instructor images. So we want to see how it performs. There's the Paris dataset with a few landmarks as well from Paris. And finally, the INRIA holiday dataset is more than just buildings. It has also other kind of landmarks. So we evaluate on all these 4. Evaluation, we use the mean average precision, which is a standard measure to evaluate retrieval, the higher the better. And first, we can look at the traditional methods. The traditional methods are the one pre-deep learning area. Yes. So before deep learning, people were using these interest points. They were using geometrical verification. And we see that we obtain pretty good results on these data sets. Now, that's the deep learning approaches. So they started really low. They were slowly catching up with the interest point-based approaches, but they're still a bit behind. Now, if we look at the results we obtain with the improvement I described, we see that we get better results than previous deep approaches, but we're even better than more standard approaches that use interest point detection. And if we look at what's happening for the same version with the distractor images, we have traditional approaches, we have the deep learning one, and then our approach is also giving the same kind of pattern, better results than both type of approaches. I think it's worth mentioning that the yellow results, that's a method that was presented at the same time as ours, and it uses also similar technique of having a learning to rank approach. That's results for 2 more datasets, the Paris dataset and the INRIA holidays. where we see similar patterns. And that's it for the quantitative results. Maybe it's interesting to see qualitatively what the queries look like. So we query with these 3 images. The query is not the full image. The query is just the content of the purple region. So the algorithm is allowed to see only what's happening in the purple region, and it needs to find relevant images in this large data set. And we see that we retrieve the same landmark, although sometimes you have very different viewpoints and you have very different illumination sometimes. So yeah, that's the kind of approach we're working with. This brings me to the conclusion of this part. So what I showed you is that deep architectures can perform well on instance retrieval if the right training data is available, and that's why we propose to automatically clean a data set of landmarks, and if the right architecture is used. In our case, we use this RMAC descriptor that pays attention to the details, and we use it inside this 3-stream Siamese network where the weights can be learned end-to-end. We see that these contributions significantly enhance deep retrieval methods, and that we obtain results that are even better than key point-based methods. And still, we have much faster method at test time, and we have a smaller memory footprint. I'd like to mention that this is a joint work with my colleagues Albert Gordo, John Almazan, and Jérôme Revaux. And if you want to know more about this work, we have 2 publications describing all the details. We had a conference paper at ECCV in 2016, and we have an extended version in the IGCV journal. So that's the end of the first part. If you have any question now, or I can move on and then, yeah.
My first question is, you said you have a 3-stream Siamese network for the non-relevant picture. How is it chosen? Is it completely random? Or?
So we do have labels, right? Because this data set is a data set of landmarks. So when I take a query, this can be completely random. Then when I choose a relevant, this is an image that belongs to the same class, so same landmark. And then the non-relevant is any other landmark. So it just has to be a different building in our case.
And it's completely random in any other...
Okay, so any random building would work. Now if we want to go to the details of how to train these things properly, to have a faster convergence, it's a good idea to bias a little bit the triplet sampling and to do something that we call the hard triplet mining. So instead of, if we take randomly any triplet, most of the time the images will be correctly classified. So let's go back. Yes. So most of the time the loss will be 0. So then we'll have no improvement and we'll have no update. So to make convergence happen faster and also better, it's a good idea to focus on the triplets that have a loss. So we try to look for non-relevant that, of course, are non-relevant, so they're a different building, but still, when you look at the descriptors, these descriptors thinks it's extremely close to the first one. And we mine for these things, we mine for these difficult triplets in purpose, so then we train better models. Yeah.
And I have a second question is, so you train mostly for architecture pictures?
Yes.
And it's basically kind of a feature extractor trained specifically for the visual research. Have you tried to apply the same, I would say, feature extractor, I don't know how you call it, to other data sets that are not architecture, I don't know, food or anything?
Right, so it's true that most of the instance level retrieval data sets that exist in the community are landmarks. So many are buildings, some are landmarks in a more broad sense. We tried with the UKB dataset that are everyday objects, and that still works pretty well. I think what is more important in that case is to have this training for ranking part and not the landmark dataset itself. So, well, we were successful to apply this model trained on landmark on other tasks. We tried it on retail products, we tried it on people, and it's already doing a good, decent job.
Without any retraining?
It was already very decent without any retraining. Now, if you have access to a data set that is more in the domain you're interested, then I would recommend fine-tuning for this domain. Because if you have data, you can have a more appropriate model, so you can really build what you need. So yes.
I have a question regarding the loss function. So how do you choose M and the margin? And second question, why this formula of like, you know, the first comparison minus the second one, not like a ratio of the comparisons more than the margin?
Okay, so the margin needs to be chosen appropriately. The margin obviously plays a role. It's a good idea to have a margin, not to have zero. But any small value would do, I guess. So that's okay. We're giving the numbers we use in the paper. I think it's 0.1, but I would have to double check the exact number. I don't think it's that critical, but you do need a margin. Now, why using this form? Well, this one is really nice for a bunch of reasons. So already the similarity is just a dot product between two global representations. So that's very efficient to compute. So that's nice. Now, why having this plus minus? This is extremely standard. So we have not invented this triplet loss. It was used by people for a few years for metric learning, for example, metric learning approaches, and it was proven extremely successful, so we started with something that worked. No, we haven't tried anything involving the ratio or anything.
Hello, thank you for your presentation. I would have a question about the network architecture for the retrieval. You have the triplet loss, and then what do you have after? I guess you get embeddings, and so like projection of your image in a special vector space. So what do you do after? Do you have other neuron or?
Okay, this architecture is used for training, right? Yes. So transforming an image into a visual signature means going through all these steps and building this guy here, that is my global representation. And now I need to look at 3 representations at the same time in order to get a triplet loss. But now the goal is to have the training happen only at train time. And at test time, at deployment time, I don't want to do any training, I don't want to have anything. So what I'm going to do is simply transform every image into that vector and go for a very simple similarity measure. And that's why I mentioned dot product. So if I go back to what we want to do, this arrow here is simply the RMAC with all the weights that have been trained with this Siamese architecture. So I transform an image into a vector, going through all these steps, all these neurons, right, that transform them into the appropriate representation. So this visual representation, you can see it as a point in the embedding space, a visual embedding space that is appropriate. And because we've built this embedding with this loss that looks at similarity as a dot product, it means that at test time, I simply need to compute the dot products between these guys.
Do you use an acceleration structure like a KD3 or?
Okay, so for the results I show here, I go for the full vector. So these guys are 2,000 dimensions, and I do a dot product.
So you compare the vector of your image with the vector of all your classes.
Exactly. Then we have a faster version that we describe in the journal. I will have no time to really go into the detail, but we have compression, and we have a product quantization compression, which is another technique to compress vectors, that allows to transform these guys into very compact representation that are extremely tiny, and then comparison between everything is extremely fast. So if you have data set that are of reasonable size, then you can still do the exhaustive comparison. If you start having billions of images, then you probably need to pre-process a little bit so you don't like go through the entire data set. And you have dedicated techniques for that. But no matter what technique you do, at some point you need to refine. Once you've chosen a set of candidates, you need to refine within this set, and that's where you need to use this. But of course, if you go to billions of images, of hundreds of billions, you need to organize a little bit your data. So compression will not be enough. But this is, I would say, beyond the scope of what I'm presenting here. This is on top. This is really something that can be successfully combined, and that is necessary to scale to Google search kind of image. Yeah. So person search. This is to show you that everything I showed before was using landmarks, but this is in fact quite generic. And that's a very recent work. That's actually the most recent thing we've done in visual search in the group. And here we are looking at the the question of person search that is also called person identification, and it's seen as a retrieval task. So what we would like to do is to retrieve the same person from different cameras. And we assume we have a person detector that has been applied, so we get image crops that contains only one person in the image, and we would like to recognize that this and this are the same person based like from this camera. This is obviously used in video surveillance scenarios, but this is also of great interest in ambient intelligence scenarios where, for example, if you interact with a robotic platform, you would like this platform to remember that you already had a previous discussion with it. This is a retrieval problem again, where everything boils down to getting the right representation. If you transform your image crop into the correct representation, again, you can just do this dot product, very simple similarity measure, and retrieve the right person in the dataset. I'm going to skip all the details about the method because it's extremely similar to what I showed before. There's a few specificities because if it's about people, but we're still using this 3-stream architecture to train. Now, I'm going to show results on 2 datasets, the market dataset and the Duke dataset. The first one has 6 cameras, the second one has 8. What I would like to mention is, look how the variability of appearance you have. Sometimes you have the detector that completely crops part of the person, so it's truncated. Sometimes there's a lot of background that you don't expect, so the scale can be very different. You also have different viewpoints. People are, you see them from the front or from the back. Sometimes the pose is different. You have this person that is sitting on a motorbike that you need to recognize when it's standing later. So the pose variation can be important. And yet, sometimes only tiny details allow you to differentiate between the people. So we really need to learn a representation that can capture all these details. And we're doing it simply by having this RMAC descriptor that pays attention to the details, together with this Siamese architecture that is looking at how to rank things. These are existing results in the research community that were all published this year, if I'm not mistaken. And most of them were focusing on solving this alignment issue. Exactly the one I mentioned about people being truncated or the pose being different. Some use part detector, some use pose estimation. And in our case, we went brute force, no such thing, global image description, but trained. And these are the results we got. So just to show you that this approach is very generic and can be applied to other things than just landmarks. This is to show you queries where it works extremely well. So you see the query image, you see the top results. Here it's showing the mean average precision, the average precision for the query. So we see that the images that are relevant are ranked first on these examples. And what goes next are different people, right? And here are the failure cases, the worst examples for our algorithm. And we see that it's quite difficult to differentiate these people. They really have a lot in common. They have the same clothes, and I mean, even manually, even human annotators would have a hard time solving this task. Here, typical failure case on that one image. The clothes are hidden by the backpack, so there's no way the algorithm is going to look for pink, so it's looking for these black shorts. So that's the kind of failure cases we have. What is interesting to look at is what are the regions that matter when matching pairs of images. Because we've seen that all the other approaches were improving by doing some explicit alignment mechanism. So in our case, why can we do this so well without any explicit matching? And to visualize that, we use the GrabCam algorithm. That is an algorithm that was proposed a few months back at a conference. And this algorithm is looking at regions that activate certain dimensions. So now I said that the similarity is computed using a dot product. We can see which dimensions contribute the most to the similarity, and we would like to see which region in the image activate these regions. And we get these kind of maps. So we can see what it looks like. Here we have this 2 images where you see you have quite a strong scale change. And you have this neuron that activates here. And on the bottom image, it seems to activate on the same thing. By same thing, I mean here the backpack and the shoes. The second neuron will focus on the hair and a little bit the backpack as well. And you can see that even though images are showing the person in a quite different angle, these regions tend to be consistently firing in the same location respectively to the person. So we do have some kind of alignment mechanism, I would say. Here's another example where you have many of these strong firing neurons, the one that really contribute to the similarity, that focus on the bag, because it's a very important thing. But the bag is barely visible in the second image. Well, what's interesting is to see that the algorithm has learned to match the bag and the shoulder strap, which is also seen here, where you have the bag and the shoulder strap. So it's learning to align, but not only the pose, sometimes the semantic when there's things that are occluded. So it's only visual inspection, but I think it's reason to believe that the algorithm is doing this implicit alignment, and that's why it's working so well. This brings me to the conclusion of this second part. So we've considered the task of personal identification. We've showed that this three-stream Siamese architecture is well suited for the task. We see that we didn't use any pose or body part detection, but still there's some kind of alignment happening between images. And this is joint work with other colleagues at Naver, John Almazan and Naila Murray, and Brena Bajic did an internship with us for a few months. And you can find more about this work in this publication. This brings me to the end of the second part. Is there any question on this second part before I move to the last one?
How does this algorithm fare when it comes to monochromatic images, given the prevalence of monochromatic surveillance cameras?
Oh, if we forget about the color information, right. I think it would have a hard time from a model learn in color, because we've trained a model to use all the cues it has access to. So if you train a model for color images and suddenly give it only black and white images, I think it would have a hard time. So you would have to retrain your system with the kind of data you expect. So maybe, yeah, like gray level images or an infrared image or whatever you want to use as an input. But I think if it has seen some kind of images at train time, then it will learn to focus on something else. If it doesn't have access to the color information for differentiating the images, then it will have to pick up on other cues, textures, and we haven't tried, but I think it will learn something different. Yeah. It would have to be retrained for your task in that case.
Thank you for this second part. I have a question about maybe an issue with this re-identification. I guess it works when the person has the same clothes, but when the person has not the same clothes, then you have to then you don't know anything about the you cannot really identify the person. So can you focus on the face of the person and try to recognize from the face only, or is it too difficult? Have you tried? And if you didn't try, do you know any data set that are suited for this task?
Right, that's a very good point. Here in this scenario, we assume that the person is not changing clothes, or maybe just removing a jacket or a backpack. So we are relying on all the cues we have, like the entire body appearance. And of course, if you change clothes, you fool the system completely, right? Now you would have to focus on faces. I don't think we have the kind of resolution needed for this task on this data set. Now, I really think that this kind of approaches with learning to rank is really suited for faces. But then you would need proper training data. And there exists a lot of data sets where you evaluate faces, like identity of people. You would need the right resolution, but there's nothing new there, because I mentioned that this ranking loss was known for other tasks, and was known for metric learning. And actually, that's one of the very first applications of metric learning. People really use these metric learning approaches on top of face representations. So I know it's been done in the past. I know it's working very well. And this learning to rank approach should work extremely well for faces, even in real applications. Yeah. So now let's look at a problem that is slightly different. I mentioned traditional image retrieval, and most of the time when people target image retrieval, they look at the instance level retrieval task. So you give an image that contains, in general, one object. You're interested in that object, and you want to retrieve the same object. Possibly very different conditions, but still the exact same object. But now, what if you query your system with such an image? So we have a complex query with many things happening. Well, you don't really want to retrieve the exact same object. Doesn't make sense to retrieve the same t-shirt, right? That's probably not why you query this data set. Or the same ball, or the same face. What you probably want to do is to understand what's happening in that image, the fact that you have this little girl that is playing the football with a man, probably her father. And once you've understood that, you probably want to retrieve images where the same things happen, the same kind of activity, the same kind of interactions. So basically images that tell the same story. But as you can see, images visually, they're very different. That's only because you understand what's going on that you can say they're relevant. So that's the task we're going to look at now, and it's called semantic image retrieval. Sounds like a subjective task. So I guess that's the first question you will ask me. Is the semantic retrieval task well defined? Does it even make sense? Can people agree on such a difficult and high-level task? And when we started, we were not so sure, so we decided to evaluate that properly by conducting a human annotation campaign. So we cannot ask people to rank plenty of images on how relevant they are semantically to each other. That's a bit painful. Instead, we decided to simplify the problem a bit and show people image triplets. So we show them one image, that is a query, two options of two images that are potentially similar to that query image. And we ask the people, well, which of these two images is more related to the query? As you can see, it's a subjective task. You might not all agree on the outcome for that particular query. So it's interesting to see what people say and how often they agree. The user study we conducted, we did it on 35 annotators. And we covered in total 3,000 image triplets. And we computed a leave one user out agreement score. So for every user, we see how often this user agrees with the others. And we have an agreement score, and we do that for all the users, and we average. So this is our final evaluation measure. And on these 3,000 triplets, we see that people agree with each other at 89%. So obviously, that's not 100%. The task is subjective. So people cannot always answer the same thing. But there's a fairly large agreement between people. So one might say that it's a task that is defined well enough for what we want to do. Okay, we've seen that people kind of agree on this task. Now, what can capture this semantic information? If we want to automatically guess if two images are similar or not semantically, what can we use? So then that's the second study we did. We did a study on the visual genome dataset. It's a nice one because it has 100,000 images, so it's fairly large. And on top of that, it has very interesting annotations. It has region descriptions, so people have described, like it's actual people that describe what's going on in the images. You have object annotations, so people drawing bounding boxes on objects in the images, saying, oh, I have here a person, a car, whatever. And that's very useful for our study. So what can capture semantic information? The first thing, and the obvious thing, is a visual representation, a standard one. So we take an image, we transform it into a vector, and this vector is a visual signature for our image. If these visual signatures are close, are the images going to be semantically related? Is it true or not? As a visual representation, we used the one I presented before, this RMAC descriptor, and we use it pre-trained for classification on ImageNet, because it's a very standard thing to do. The second thing we looked at is the object in the image. We are lucky we have a notation that tells us exactly what kind of objects we have in each image. So we build a histogram of objects where we simply count how many of each object class we have in each image, and this histogram is our final representation. Now, if two histograms are similar, does it mean that the images are semantically related to each other? Let's find out. The third thing we have access to is human-generated captions. I told you people have annotated images with descriptions. Now we take the text, we go for a very basic text representation, the bag of words representation, which means that we just count for every word how often it appears in the captions. That's a representation for the image. So now if the bag of words representation of the images are similar, does it mean that the images are related? So that's the study we did. For the evaluation, we compare the ranking produced by each representation. So because we have this representation, we can compute similarity between them. And each of these representations can also choose one option in the triplets. So we let the algorithm choose. We compare to the choices of the human annotators on the 3,000 triplets, and we see how often they agree. If this representation agree with the human annotators, it means they capture well semantic similarity. So let's look at the results. First, this is our upper and lower bound. Human annotators, remember, they agreed with each other at 89%, which is probably the best we can obtain. Random value here is 50%. Now if we look at the visual baseline, that is the visual representation that has been trained to classify categories. And if we look at this histogram of objects, that is counting how many of each object type I have in an image, this is getting more or less the same results, around 63, 64%. This is not bad. This is much better than random, but it's still far away from this 89%. What is better, though, is the human captions. If you look at the text, if you assume you have captions for your image, and you use that, you can predict better if two images are going to be semantically related or not. You get this 76%. So out of all the things we tried, what captures the semantic information the best is the text. That's the caption round. That's very nice, but we cannot assume that we have access to text all the time, right? Because in real life, you will not have human-generated captions of your image describing everything that is happening. So can we build a visual representation that is as good as the text for this task of semantic retrieval? And how are we going to do that? And we have at least the text for some images, because that's the data set where we did our study. So we're going to assume that we have human captions at train time. We're going to use these captions as privileged information. And we're going to leverage human caption as a proxy for semantic similarity. Because we cannot make training data with real annotation from people. We will never have large-scale enough data. But we have quite a few captions on this data set. So now we are going to leverage the captions on this data set to have a proxy ground truth that is not perfect, but it's already decent enough. And we're going to leverage that to train a good visual representation. So let's look at what the captions look like. Maybe it's a bit small to read from the back, but okay, let's look at the first image. We have a boy jumping in the air with black sneakers, a skateboarder doing a trick, a skateboarder in the air, and concrete skateboard ramp. If the text is similar, it means the images are semantically related. At least that's what our proxy ground truth tells us. I colored the words according to the, well, this like this, because remember we use a bag of word representation. So if you have the same color, it means the captions are similar. So now we're going to look at when the captions are similar and when they're dissimilar to decide if our images are related or not. And we're going to leverage that to build a visual representation. So we're going to build a visual embedding. So we're going to build visual signatures that land in this visual embedding. And what we're going to do is, if two images are considered similar according to the captions, we want them to be close in that visual embedding space. Now, if they're very different according to the text, we want to push them far apart. And we have many of these constraints because we have an entire data set for which we have captions. So we're going to try to enforce all this. And if we represent appropriately the space, hopefully it will generalize well. So remember, we have the text only at train time. But at train time, we can leverage it. At test time, we have images only. There's no text anymore. But if we train this embedding phi to build a good visual embedding, so to build a good visual fingerprint, then we simply embed the entire data set, so we embed all the images. We embed our query image, and then if the embedding is good, we just look at the neighbors in that embedding and we retrieve the closest. So the closest image in this data set in the embedding is this guy, and that's what we want to achieve. So that's building a visual embedding. What does it mean in practice to ask these images to be close, and what is this phi? Well, this is going to be very similar to what I presented in the first part. Again, we're learning to rank. We are going to leverage this 3-stream Siamese network. So this is a training architecture that looks at 3 images at the same time. A query, a semantic query, right? A relevant image and a non-relevant image. We have this representation that is, again, the RMAC, that is producing one global representation. And then we're going to look at this representation in a loss. So the phi function that is defined here is actually this process to go from one image to the global representation. And that's what we're going to learn. So the triplet loss is something we've seen already before. So it's taking into account a query, a positive and a negative image. And it's looking at the similarity between the query and the positive and between the query and the negative. And this is the same as before. So that's how we can build that space. If we enforce the constraint, we have such a visual embedding. The text was used only to decide if 2 images are semantically related or not. And that's already good because it gives us the constraints. But maybe we can use the text even better. We have text only at train time, but we could also try to embed the text. So it means that we're going to try to build a joint embedding for text and image, where we have this phi function that transforms an image into a vector in that embedding space. But we also learn a theta function that will transform the text into also an entity that lives in the same space. And we can add more constraints. So instead of asking these 2 images to be similar in the embedding space, so these 2 blue points to be next to each other, we can ask this image to be close to that text, so this point to be close to that one, and that text to be close to that image, right? So this point to be close to that one. So we can enforce additional constraints. Of course, again, at test time, we have no text. So it's not going to help us at test time. But maybe by using this information at train time, we also train a better representation. Also, we'll see that having a textual embedding is going to be interesting for some applications. So how do we do that? We have, again, the same architecture, except that now, instead of having only a visual loss, we have 2 textual losses that are the cross-modal losses I mentioned. So that's the visual loss exactly the same as before. That involves phi, but now we are going to have 2 textual losses that involve phi and theta together. So if you look here, we have only visual information, but now we have this cross-modal information where image and text are forced to live together in the same space. So this is where the magic happens for having a joint embedding with image and text. Obvious question, well, does it perform well? So our evaluation we did on the visual genome. This visual genome is the one we use for training. So we split it. We use 80,000 images just for the training, where captions are leveraged, because we're allowed to use them for training. For validation and test, we have 10,000 images, and we don't use text. We don't use text at all. We just look at the images. And for the evaluation, we look at the evaluation based on the triplet annotated by humans. So we are going to see what these visual predictions in the embedding space says about what is similar to what. We are going to see if it matches what the user said. So that's how we evaluate our system. And these are the results we got. So again, upper bound. Upper bound is if we were cheating and having access to the text. If we use the text to decide if 2 images are similar or not, remember the text is getting us this 76%. Random is 50% again, because this is the same measure as before. Then we have a visual baseline. So this is our visual representation without any training, the original one. We have this Wasabi method that is the closest we could find to our approach, that is giving better results, but still not so much better than the visual baseline. And these are the results we get with the proposed embedding. So if you really train a representation to be good at this semantic matching problem, then we see that you get results that are on par with your caption ground truth, right? Your proxy ground truth you train with. So we really managed to close the gap between what we train with and the purely visual representation. So we don't need text anymore for that particular task on the data set. And we see that there's really little difference between the purely visual embedding and the joint embedding. So at least for the evaluation purpose, there's not such a point for text embedding as well. Let's look at qualitative results, because it's interesting to see how the training affects the results visually. Here's a query image where you have a couple that is cutting a cake at a wedding. And you see the top retrieved images if you use the visual baseline. So this is standard representation that is not trained for this task. Well, you see that already it's doing a good job. It finds things that are similar. You have people, you have plates, you have ties very often. They're relevant, but they're not exactly matching the story you want to tell. Now, if you look at what's happening after training, you see that these images are a bit better. You have most of the time couples, they're in more formal environment. You even have sometimes people at a wedding cutting a cake. So it has captured some of the semantic of the scene to retrieve the right images. Here is a second example where you have this person that is playing the frisbee, and you retrieve people that are in a field doing all sorts of activity. After training, you get people doing the exact same sport, playing the frisbee. And now, why does it make sense to have a text embedding? Well, in our data set, we still have no text. Our images are alone, no caption. But maybe if you query with an image, you can also combine with a textual query, right? So if I just query with this image of a man riding a horse, I get more people on horses. But now if I embed the word horse, and I embed the word elephant, and I do this kind of arithmetic, I can get this kind of results. So I have people on top of elephants. So having a textual embedding allows to really refine the queries. So this is a fun and striking example. They're not working as well as that one, but in many cases, you might want to refine your query with both modalities, image and text, to refine your results. And that's really a realistic application scenario. This brings me to the conclusion of that part. So we defined the task of semantic retrieval. We showed that there's a large inter-human agreement on this task. So it's an interesting one to study. We've seen that human captions are a good proxy for the task. And they predict well what people are going to tell you is relevant or not for the semantic. We've seen that we can build a good visual representation for this task. If you leverage the captions at train time, then you can build a representation that is good at test time even when you have no text anymore. And we've seen that if you build a joint embedding for image and text, then you can jointly query with images and text. This is a joint work with Albert Gordeau, and this is a paper we presented last summer at the CVPR conference where you can find more detail. And this brings me to the very end of my presentation, so now if there's questions for this part, I'm more than happy to answer them.
I'm sorry if you already said it, but how do you process human captions? And the second question is, human captions become one of the most important things for this method to work. And if how are these captions written? Is it the same person? Because maybe it's the subjective part of the work doing the captions, because someone will talk about the skateboard and another one talk about the boy, but it depends on the human writing the captions. So.
That's a very good point. So there are two questions, right? The first one is about the representation. Maybe I can answer the one about how the dataset was created first, right? I think it's really, really important to go to that point. So this is a visual genome dataset. So there's not one single annotator. It's an initiative that started in Stanford, and that's Li Fei and many colleagues that work in our team that work on this. and they collected this giant set of images, and then they used the Amazon Mechanical Turk to get it annotated. So it had been annotated by a huge number of people. They probably have the exact number and the distribution of the number of people per image in their journal paper. But I think there's two things that are interesting. People had to do the captions in a certain way. So people were asked to annotate something, to describe something, and then the next person coming was asked to describe something else. And they really searched for diversity in the descriptions. And the more people were adding things, the more difficult it was to be original compared to the others. But I think they had this interface that showed, I think it was the 7 most popular the captions, so people try to go for something else. So as a result, there's a large diversity in the vocabulary used and in the level of English, because not everybody is a native English speaker. There's diversity in what is described, because people were trying to describe something else because it was part of the requirement. So once everybody has described this first guy and this one, people have described the second guy, then people started describing what's going on in the background, this ramp, etc. So that's good because it's covering a lot of what's going on. And that's exactly why it's so good. Because instead of focusing on 2 or 3 captions that describe only the main interaction in the scene, we had something that was really covering a lot of what's happening in the image. Which now helps me answer the second question. Okay, I removed it from the slide, but we actually compared many different textual representation. Okay, so that's on the paper, and that's not anymore on my backup slide, I'm sorry. But we tried many representations with the human caption. First, we started with something quite complex that people use a lot into captioning. We use a meteor, many-to-many matching between all the representation, because when people evaluate captioning, they use this meteor measure that is supposed to capture a lot the way people perceive sentences. And that was our first try. We got a number with that. Then we used a word-to-vec embedding, because maybe people use different words to say the same thing, and you want to have something that is more normalized, so you embed your word in the word-to-vec embedding. And on top of that, we use the Fisher vector representation. And then we went for the simplest, bag of words. So we have a large vocabulary of everything we have, and we simply histogram that. We do a TF-IDF to reweight the words, because you want the more frequent word to not take the entire credit for the similarity, so you want to downweight them. And surprisingly, a bit, what worked best was the bag of word representation. And I don't think it means that the bag of word representation is better and the other one are not good. I think it's because of this data set. Because we had so many annotations. We have in average 50 region level annotations. So because we have so many of them with so many different ways of describing the same thing over and over again, people have I've used all sorts of words and they've covered everything. So you don't really need fancy word-to-vec embedding because you pretty much have everything. So I don't think it means it's bad for something else. But in our case, bag of word was working surprisingly well. I think, it was in the range of 72 for Meteor and something like this, right? Not that bad, but a few points below. Yeah. Did I answer the, yeah?
Thank you.
Merci.